Hi guys, welcome to section 3.2 on confidence intervals. So there's quite a bit in this section. Well, actually, this section is kind of a setup for what's coming, the mechanics of it. This section is trying to really explain the idea of margin of error and confidence interval from more of an intuitive perspective rather than getting too much into the mechanics. We'll get into some of the mechanics, but I want you to put a lot into this to try to get a clear understanding of what's going on. So I want to look at one thing on the Wiley Plus before I get into this. So I'll do a video lesson and I'll do some examples and such. But I wanted you to recall that if you go to section 3.1, or in this case 3.2, understanding and interpreting confidence intervals, you can click through and you can get to this learning hub once again. Now if you click on the videos there, you'll see some video tutorials of specific learning goals of some of the examples in this section. So those are really helpful and detailed. You know, again, if one seems pretty straightforward to you, you can skim through it. Otherwise, you know, pick a few, see what works. But in particular, this interactive lecture is actually quite good. So if I click on this, and then hang on, I want to make this larger. And there it is. I can make it larger, but I think this is still open. All right, so you can click on this.
In this video lesson, we'll discuss section 3.2.
We'll take you through, but the nice thing is that it will pause at times. And so the question is, the higher the standard error of a statistic, the blank, the uncertainty surrounding the statistic, higher or lower. So you can take the quiz now and you would stake your answer, higher or lower. So the higher the standard error should be the higher the uncertainty. So we submit that and it's correct. We continue. And then it will continue on with the lesson. So there are a few places along the way where it will prompt you for a little quiz. And that's a good check of your understanding. It also get into some examples that I won't necessarily talk about. Not necessarily heavy on biostats, but the sections 3 and 4 are really getting at the mechanics or the ways of thinking about inference. So the specific application isn't as important as it might be later on when we're talking about data analysis. All right, so I'm going to close that though for now and open up my notes for this section, and we'll go ahead, but you'll see there are quite a few links here, some activities, and just a few articles. Actually, let me show you just the beginning of the notes here, and then we'll get into something in particular. So understanding, interpreting confidence intervals. So confidence intervals are giving an interval estimate, a range of plausible values for a population parameter. So around election time, or if you're reading results of scientific studies, you're often getting an interval estimate for what we think is the strength of some effect, and it's usually framed as a statistic plus or minus a margin of error, or the article will state the specific confidence interval. So I want to go back and click on a few of these links, so hopefully you'll be able to access those. You might have to authenticate through K for one or more of these. It looks like this one might want me to authenticate. So this one was kind of interesting, asking for identification in retail tobacco sales to minors. So it was a study done of they were trying to figure out the extent to which people were asked for ID. And a previous single county study found that retail stores usually ask young-looking tobacco customers to show proof of identification, but a large proportion of illegal tobacco sales to minors occurred after the customers had shown identification proving they were too young to purchase, so they were still sold. But what I wanted you to see was that just in the abstract of this, we get an estimate for the proportion, and then there's attached a 95% confidence interval with a sample size. Once again, estimate, confidence interval, and so on. This is a study association between, we don't need this, not now, association between celiac disease and mortality risk in a Swedish population. Another study looking at risk celiac disease. So findings, here's the estimate, and then there's a test of significance. Here's the results. Confidence interval being reported for the particular effect size, or HR in this case, hazard ratio, which is typical of an epidemiological type study or medical study. And timely, compassionate use of remdesivir for patients with severe COVID-19. So if you've been following the news on this, you may have heard of this drug being tested. And so this is a compassionate use study. So let's see what that means in case you haven't heard that term before. We provided remdesivir on a compassionate use basis to patients hospitalized with COVID-19. It talks about the specifics, but patients received a 10-day course of remdesivir consisting of 200 milligrams followed by 100 milligrams for the remaining 9 days, and it's based on data from patients who received it during this time period. So 61 patients received at least one dose. Data from 8 could not be analyzed, and then it gives us the results. But you'll notice something is missing here. So there's no margin of error, there's no confidence interval, there's no hypothesis test. Why? Well, these were available patients. It was not a randomized study. There was no control group. So this is just descriptive statistics. So going back to chapter 2. So I wanted you to see that, there are certain cases, especially in a unique situation like this with the compassionate use, because they're just trying to see what might work to address the virus, or to try to get rid of the virus. So people are given this, but there's no real statistics to be done. We know that we can't make inference, so we're just describing the information that we have so far. So the difference for what we're trying to do is we're trying to build up the techniques of inference, so for situations when we can generalize from a sample to a population. Alright, so just a few examples of how you might encounter these in your own research or study. So let's take a look. One common form of an interval estimate is statistic plus or minus margin of error. This will give us a range of plausibility for the parameter. So again, the picture that we want to continue to have in our mind's eye is that of of a population. And there's some parameter, let's say it's a proportion p. We have a sample p hat. And then we want to make inference from the sample back to the population. So what we're saying is that we would use p hat plus or minus margin of error, MOE or ME. So I'll put MOE in deference to my name. So let's see. So use the standard error to find, there we go, to find the margin of error. So how do we determine the margin of error? Well, we're going to use the standard error, the sampling distribution. All right, so let's pause for a little bit here and take a look at a couple things. First, I want to take a look at a handout on this. Oh, I was just in the wrong tab. All right, so just an example first to kind of orient our thinking. So India is home to 69.1 million people with diabetes and is estimated to have the second highest number of cases of diabetes mellitus in the world after China in 2015. In a survey of 2,499 adults 18 and over completed in 2015 in the state of Punjab, 8.3% of adults were found to have diabetes. So the study reported a margin of error of plus or minus 1 percentage point with a 95% level of confidence. So that's what we have so far. So what's a relevant sample statistic? Well, it's p hat is the notation, and it's the 0.083, the proportion of adults who have the diabetes. The parameter that we want to estimate is the population proportion with diabetes. Okay, so it would be the population of Punjab, presumably. So we use the margin of error to give a confidence interval for the estimate. So by that, sorry, wrong tab again. Let's see, we said statistic plus or minus margin of error. So let's do that. We take the statistic 0.083, and we're given this margin of error. Now we don't know where this comes from quite yet, but remember this is a percentage point, so we're treating it as a proportion. So plus or minus 0.01, which means that the interval is 0.073 to 0.093. Okay. Is 0.075 a plausible value of the population proportion? Well, this interval we're going to take is going to give us plausible values for the proportion. So it's in the interval, so yes, that would be plausible. But 0.15 is not in this interval. It's quite far from it, almost twice as high, so no, that would not be a plausible value. All right. All right, now let's take this a little bit further. Sampling distribution, this is for budgets of Hollywood movies. Sampling distribution shown for budgets of all movies come out of Hollywood in 2011 using samples of size n equals 20. We see the standard error is about 10.23, and we find the following sample means in the distribution and use the standard error to find the 95% confidence interval given by each. So we want to indicate which of the confidence intervals successfully captured the true population mean of 53.48 million. So now we're given the standard error rather than the margin of error. So we want to make the connection between the standard error and margin of error for this 95% situation. All right, so I want to pause here, and then we're going to go ahead and consider a little example, and then we'll come back to that, all right? Okay, so the example that I want to consider is a little activity. So I would encourage you to try this on your own. Flip the coin 25 times and record below the number of heads and tails. Well, so you could go around your house looking for a coin, or you could try something a little bit more fun. I mean, if we were all together, yes, we could do our flipping. But here, I've given you a link to a coin flipping app. So let's go ahead and click on that. This takes us to something I had open already, the random.org site, which has all sorts of things that are random. But in particular, it has a coin flipper app that allows us to flip virtual coins. And the randomness comes from atmospheric noise, which for many purposes is better than the algorithms used in computer programs. So we can flip a couple coins, and you can look down through maybe your travels or historic interests or whatever you might be interested in and pick a coin that looks good to you. Let's see. I'm not seeing the one that I'm most familiar with. Let's see. So I'll go with my ancestors' roots and take a Norwegian krone and see what that looks like. Flip a couple coins. So it looks like I've got tails, reverse, flip again, and flip again. So then I got heads. So what you could do is flip those 25 at a time. Oops, 25 at a time, and flip and count up. Those are a little too hard to tell the difference, actually. Some of these others a lot better, but you could count up the number of heads and get an estimate. What you would do with that estimate is fill in the proportion. So let's say that I had 10 out of 25 that turned out to be heads. Just in the interest of time, I won't count those out. I could tick them off if I were doing it one at a time, and I'd get 0.4 would be the proportion. And if you did it many times, describe the shape and center of the sampling distribution. All right, well, it would probably have kind of a bell curve distribution. If you did it many times, the center, we would have expected it probably to be around 0.5, maybe. but this is what we got for this particular case, was 10 out of 25. So let's see. The margin of error for finding a sample proportion in this situation is known to be 0.2. So what we want to do is take our statistic plus or minus our margin of error. So in my case, that would mean taking the 0.4 that I had up here and going plus or minus 0.20, and that would give me the interval. So 0.4 minus 0.2 would give me 0.2. 0.4 plus 0.2 would give me 0.6. Question is, does that interval estimate contain the true 50-50 proportion that we would expect? And we'd say, yes, it does. And we'd compare answers in the class and see what proportion of the class would get that true proportion. Now, you could call up all your classmates and carry out this experiment, and that would be great to do. But let me suggest another alternative, something that we haven't looked at too much so far. There's some great resources that come from this text for computing. Now, I want you to learn R, but I also want you to be aware of the fact that there are some useful applets around. So StatKey is the name of course, the Locke family applets that go with this book. They have a good sense of humor. A family of statisticians has to, I guess. So I'm going to click on this applet, and I hope you'll take a look at this, because this is for understanding confidence intervals. Sampling distribution for proportion. So we're going to use this to simulate the idea of sampling these coins, a sample of size 25. So if we look around here, we're going to see some things that we can edit to set this up. Now, this is set up to sample some of the data in the book. I guess we could look for a coin flip, and then we can edit the proportion and make that 0.5. Say OK. And then our sample size we can make 25 and say OK. All right, so I didn't do anything with data because we're just doing a little simulation of some of a coin flip. Now over here, make sure you take a look. The proportion here, the true proportion that we're sampling from is 0.5. But now we're going to consider the idea that we just have data. Now I want to generate one sample and talk about what this is. So this is like me flipping it 25 times. And in this case, I got 0.32 as the proportion heads. But notice over here, there's a confidence interval that's got constructed. It's the 0.32 plus or minus. So what was it? 0.2? Is that what we had? Oh, sorry, 0.2. So 0.52 to 0.12. It's about what that would extend. And so this one's green, and we're going to see that that means it contains the true population proportion. Now let's say that we had a class of 30. So we generate 30 of these. In fact, now I have 31. So notice that 30 actually are good. Wait, what's this dark line here? This is representing 0.5. This is our parameter that we would pretend that we don't know. But in each case, we get, different estimates. And some of these intervals contain. Now this one didn't contain. It just happened to be 0.72, which was kind of high. And so that missed the interval. So this might raise a question of, if we're constructing these intervals that we call 95% intervals, what does that actually mean? Well, let's generate a whole lot more. Let's say we were at a large state school and we had a sample of 1,000. Could generate 1,000 samples. Now it's kind of hard to see the picture. These red ones out here are extreme p-hat values, either too low or too high. So we notice that the coverage here says 95.25% covered. You could generate some more. That picture is just going to get worse, but it's approaching 95%. All right. So I hope you get the idea. I'm going to reset the plot. We still have 25, and it looks like it's still 0.5. Let's just generate 100. So see, 95%. Now, it won't always be exactly 95%. Sometimes it'll be 96 or 93. But the idea is, in the long run, we now have a method that's going to be right 95% of the time. And that method says start at the estimate and go one margin of error either side, that's going to contain the true parameter 95% of the time. All right, now let's go back to the notes and see where we left off here. We had this idea of the margin of error, but now let's talk about how we can use the standard error to find the margin of error. How do we determine the margin of error? Well, we use the standard error, the sampling distribution. The confidence interval for a parameter is an interval computed from sample data by a method that will capture a specified proportion capture the parameter for a specified proportion for all samples. So the success rate is known as the confidence level. 95% confidence interval will contain the true parameter 95% of the time, as we saw in the picture. So then the question is, if you had access to the sampling distribution, how would you find the margin of error to ensure this? So ensure that you had 95%. Well, let's think about our sampling distribution. If it were bell curve like the ones we've been seeing, it's going to be centered at the true parameter. But remember, one thing that we found out about in Chapter 2 was the 95% rule. It said that if we go 2 standard errors either side, or 2 standard deviations either side, that would contain the true, or that would contain, 95% of the data would fall within 2 standard deviations either side. All right, that the data would fall 95% of the time. So P plus 2 standard errors and P minus 2 standard errors, or if you like, if this were 0.5, then this interval 2 standard errors either side should contain 95% of the probability. So this 2 is the right number of standard errors. If we got a p hat out here, outside of this range, then if we tried to construct a confidence interval, 2 standard errors either side, we would miss the parameter. But most of the time, the 95% of the time that we're between the 2 standard deviations either side, we're going to contain the true proportion. So what this is saying is, at least for the 95%, we have a recipe, which is to take p hat and we add and subtract 2 standard errors. So the p would be, if we knew what the true proportion is, we don't in practice, so we take our statistic and we add and subtract 2 standard errors either side. So the margin of error for 95% is 2 standard errors. We'll see later that other values of confidence are going to correspond to different multipliers, but 2 will correspond to 95%. So if it's symmetric and bell-shaped, a 95% confidence interval is computed in the way that I was just showing you. All right? So here's the picture really that we were just looking at. Now let's go back to the example that we had left off. So we wanted to get a 95% confidence interval. We have a standard error of 10.23. Here's the simulation that was computed using StatKey. We could have just as easily done it the way we were doing those in R on the last screencast. So we could take 40 plus or minus 2 times the 10.23, and that would give us an interval. Okay, now I'm going to fill these out for the 3 and then be right back. Okay, I went ahead and filled in the calculations. So I add and subtract 2 times the standard error in each case to the statistic, the estimate that we got. So again, why do we have several different estimates? Well, we're considering hypothetical estimates that we might have gotten and just want to connect what's going on when we compute the interval compared to the true mean mu that this is generated from. So the population has a true mean of 53.48. We took a sample of 20 from all the movies and got different possible results. Constructed intervals, and this one would be good because it would contain it. This would be good. This one would not be, because 53.48 would not fall in the interval. Such a high value out here is going to lead to an interval that's not going to contain the true parameter mu here. Okay. Where the others, like 70, if we started at 70 and went 2 standard errors either side, we'd get an interval that would contain the true mean. So it's this idea that when we take a sample, we're just going to report one interval, but we want to understand what it means in terms of this coverage property or coverage probability. Okay, so for each of the following, use the information to construct a 95% confidence interval and give notation for the quantity being estimated. So I'd encourage you to go ahead and try that, and I'll fill in the answers for you, and then you can come back and check. Okay, I've gone ahead and filled in the values. So p hat equals 0.72 with standard error. So here's the standard error, here's the standard error, but here's the margin of error. So in this case, we're adding and subtracting twice the standard error to the statistic. All right, so I've got intervals computed that way, twice the standard error in each case, added to the statistic. And then in this case, our statistic is a difference in proportions. The margin of error is given. There's no multiplying by 2 that has to happen. So we've got the stat, in this case, plus or minus the margin of error. And then we calculate 0.03 to 0.07. And we might observe that we're 95% confident that the difference is greater than 0, or that 0 is not in the interval. And if we're comparing two groups, that's an important thing. We don't think that 0 is plausible. So it's unlikely that the proportions are the same for the two groups. All right. Well, I think I'll stop here for now and then start a second screencast so you can join me on that one. All right. Well, I hope it's starting to make sense. Again, go back and work through areas that you're confused about, and I'll catch you on the next one. Take care and thanks for listening.